Honorable Director of this institute, Professor, delegates and student friends. Let me congratulate NIT Jalandhar for organizing this conference on the theme which is most important in today's world, energy and environment, and of course together with biotechnology or biological processes. I'll just give you one example that in my department also, during establishment of master program in membrane and separation technology, I have installed, there was a well which was abandoned, and I realized that we can really make use of this well, and I installed a windmill on that because electric line was not possible. So I installed a windmill there, and using the mechanical energy, I collected good amount of water in a sump, and over the sump I put a 1 HP solar pump. And using this solar pump, that is 10,000 liters per hour capacity, having 13 meters head, I used to run experiments on fluid mechanics, where you know that you need lot of fluid flow for your experiments on orifice meter, venturi meter, and so on. Similarly, when I realized that we can really make use of these solar plants for creating distilled water, which is required in laboratories, that also I could save a lot of energy. And when I made the energy calculation, I could save good amount of energy and money throughout the year. So basically, when you really make use of hybrid technology, and then we have developed the technology that is now, if you see any chemical process industry, downstream cost is contributing something like 70% of the total cost. What is required that you need to optimize the downstream processing by coupling various technologies, whether it is separation or concentration technologies put together, it goes up, and hence the productivity goes up, production cost goes down. So with all this requirement, that whether the energy conservation together with, as you know, the biological process has really a chemical energy store. So imagine if we have to really develop a system which is energy efficient, which is also energy conservating, and also which is different forms of energy that can really meet our energy demand. And that is going to be, of course, hybrid system, whether it is solar, wind, biology, and finally energy security through bioeconomy is the now world, and every country is planning for energy security by creating a right mix of energy. So I congratulate NIT Jalandhar for organizing this international conference, and also I welcome the delegates.
Thank you, sir, for your precious
words to thank our dignitaries for gracing the occasion and sharing their valuable knowledge with us. We would like to express our gratitude by presenting them mementos and shawls.
Look here. Thank you. Wait. Answer, look here, good. Thank you. Hani sir, ठीक है, good. Thank you.
What happens in the year 2011, this Indian Institute of Chemical Engineers Global Regional Center, so they have given lifetime achievement award to two persons. First is Dr. of Auburn, and since he is not here, so I request Professor Palanki he will receive that honor in his absence.
Answer, look here, good. Wait. Okay, good. Thank you.
And the another institute also he has significantly contributed in setting up rubber testing laboratory and then many more. So because of the time and all these things, we are not taking much time.
Answer, good. Look here. Answer, looking good.
Thank you.
Invite our organizing secretary, Dr. NIT Jhalandhar, to deliver the formal vote of thanks.
Already late, so I will not give much about all these things for thanks. The only thing is again, once again, I convey my sincere thanks to Professor Ram delegates also for attending here and all these things, for organizing this inter-year session. And since I am not a part of a vote of thanks in any, so I am not able to give our sincere thanks to our director also. Who did all these things. He never did whatever we have written, he only sees the signature and he put his signature. So that kind of thing, I can say confidence and all this is something due to all these things. Okay, thank you.
At a tea break of 10 minutes have been scheduled outside the CSH, and afterwards the session will be held at first floor IT Park. We will proceed. Another announcement is the annual general body meeting of IICHE will be held at ground floor IT Park at 5:45 p.m. Thank you.
And we'll see how we can come up with stuff that's actually pretty interesting and can lead to publications and can lead to funding and things like that. Alright, so the talk is divided into 6 parts. So we'll have an introduction and I'll talk about a systems overview, and then we'll look at design issues and then some simulation results and then some future work. Alright, so we're talking about the hydrogen economy. This is in the news. People are talking a lot about the hydrogen economy, and you have the chicken and egg problem. You cannot have cars that run on hydrogen because hydrogen is not available, right? There's no gas station, there's no petrol station you can go into and fill hydrogen. And we are not going to sell that because there are no cars that you can fill in. And so what we were looking at essentially was, this is an issue, this is an infrastructure problem. And so our idea on this basically was that we are going to look at using conventional or mobile applications. And once that technology matures, maybe the part which comes from fossil energy can go away, and then you're completely on the hydrogen economy. So this is sort of electronics, so sort of small scale, stationary power. Now I live in an area where we get a lot of hurricanes. So this is always an issue. When the hurricane comes, you're camping out, or if the power goes out, then you need a means for stationary power also. Okay? And then of course the big market is the automotive power. So if you're running cars, then could you run them on hydrogen? That was the motivation. So what we wanted to do, and the constraint we sort of had was we were going to use equations that are taught at an undergraduate level only. So we're going to keep it very simple. Okay? And so here are some issues that sort of come into this. The fuel cell, so typically the carbon monoxide. Okay? And then there are issues of which sort of fuel cell, is it a polymer electrolyte, which one would you use? So again, each of these are issues. And so what you can, again, if you think in terms of, and we can give different hydrocarbons to different students, different fuel cells to different students, and we can kind of mix and match and see what happens. Regime will dominate. If they are large, then diffusion will dominate. Again, stuff you've seen your reaction engineering undergraduate course. So there are a large number of parameters that you have to estimate. So there are some lab scale experiments one has to do and develop this. And if you look at the models that are available in the literature, they tend to be sort of like this, right? So there will be denominator terms. It will be sort of Langmuir-Hinchelwood type of kinetics. And so if you look at, so once you have this,
if you found the consequence, either how much thermal blast or how much toxic concentration, if we combine the fatality and the fatality per event or event per year, the probability and consequence and multiply, you can get the risk. Similarly, the risk if we in India, as I have already told, in India we don't have any number. For example, in Netherlands or US EPA, if you go even have a 10 to the minus 4, and how we can find out for any chemical engineer plant design, we can fix the number. So that is the risk criteria. And once we design the plant, if the number exceeds a certain number, then we have to modify the design, and we have to, if the number crosses the limit, we have to redesign. And even if it is the risk is less than the desired value, then of course. So if that amount of chlorine comes, how to take care of that kind of plant? It is happening in the public area. It can happen in the chemical industry as well. So if that is then what should be the safety system should be available, personal protective system should be available. So that we found that even the nearby college people, college student, and the some hospital area and some population density, if it is high, people can get affected. So I will show the analysis how we have done next. So this is the scenario. You can see the chlorine cylinder how it has slowed down. Mostly fire people came. They didn't know how to already told. Next. Now because of porosity of time, I just sort in the description. So there is a dispersion. So any chemical, when it comes first is the source model. The Gaussian dispersion model is normally used for the light gases. And if it is chlorine is heavier than air, obviously it is a heavy gas. So it is a heavy gas model used for the analysis. Next. Now there are certain models. Of course, we are doing a lot of CFD models. The pipeline is we have assumed that 2 mm leak in the body, or another is the pipeline whatever it is connected. Normally the nozzles. So 15 mm nozzle leak we have considered these two scenarios. Next. Now this is the Ritter backward model. This assumes this some dimensionless quantity, which when it is greater than say 0.15, that half G0, Q0, all these things, mass flow rate and wind speed and everything we consider, that was processed in one time, that is a heavy gas. So within this correlation we can find out is how much distance the toxic concentration can come and what is the concentration.
Have not seen what this electricity is. 80% of the population still cooks with the biomass, agriculture residues, cow dung, etc., etc. And they are living in a very pathetic situation. We did the analysis. You see, I had developed improved cook stoves, and 7 million of them they have been used in India. But then that particular stove, you see, program has women who are working in the kitchen. The most polluted atmosphere is the rural kitchen, and they are exposed to the pollutants equivalent to smoking 200 cigarettes a day. Hanging from the roof, and the amount of the carbon is mind-boggling, and it has been calculated that the major cause of mortality and morbidity is because of the smoke which is there in the rural areas, eyes and etc. Now we did a calculation that if that 80% of the population we have to give the LPG, such a big scarcity, and if we want to give it to them, only God knows where we are. So that is the real challenge for the problem. And number 2 is on the economy. With a meager amount, with a very meager amount of the oil, which we are using as compared to any bigger developed country, 100 crore rupees on the economy, and that is what is the killing aspects. And as the prices have gone up, the economy is really. And the next one, please. So there is now one is the availability. I have given you the picture of it, that there is a big gap, and this gap is going to increase. We will move as far as on imports is concerned around 90+% by 2025 for the oil, and maybe 40. Availability of energy in varied form in sufficient quantities and reasonable prices, and new concepts have been reliable and energy at afford on the basis of protection of economic security and the environmental security that has come into picture. Next one, please. So this is the scenario. You see, now most of in the Kyoto Protocol calculations, in the Kyoto Protocol.
Oh, that's all right.
Thank you.
I would like to thank your great hospitality. I think it comes from your several thousands of civilizations, as I can summarize. The talk is on the dye-sensitized solar cells. It's a couple of years that I have been working in this area. In particular, I've been working with Ken Lau. He's an experimental. Was my PhD student, graduated and joined Brewer. Siomek was working with Ken, and also he graduated and joined the Brewer. Today I'm going to present some expertises in electrolyte synthesis. So we have a team of 2 experimentalists, and myself is modeler and simulation and systems person. So this is outline of my talk. I'm going to start with an introduction, then model development, present some steady-state simulation results, IV curve prediction, simulation of transient response of the system, and finally some concluding remarks. Basically, the dye-sensitized solar cell consists of an anode, a dye, an electrolyte, and a cathode. There are other parts, but basically goes out and goes to the circuit and comes from the other side, and then the electrolyte is responsible for carrying the electron to the anode side through the cell. The idea was first introduced by Gratzel in a paper published in Nature in '91. This type of solar cell. So once you replace it with polymer, then that issue will be.
Which ions will be transported through the polymer electrolyte? The iodide ion?
No, these are new polymers. So we are developing them. Okay. Yes.
Notice that the different models predict right constant, the actual right constant, many order of magnitude different.
Right.
Why is that?
Because the type of equations are significantly different. And they are based on different mechanisms that you assume, and they are based on assumption that which reaction is faster than the other one. So in one is dominant, the other one, the second one dominant. So the equations that I showed are different from each other. Slide 9.
Number 9.
Assume that electric field is not important, then this becomes 0.
Okay. Any more questions? Last question.
this model says that the generation of charge separation takes place at that plane. That what is the topic?
Separation exponentially decreases as light travels inside the cell. All right, let's thank our speaker one more time. Thank you. Thank you.
Explain yourself, look here. Okay, good. Thank you. Answer. Okay, good. Thank you.
Mr. Chairman of the session. I'm thankful to chemicon 2012 organizers who gave me the opportunity. India, role of fossil fuels and renewable energy. All of us know what energy security means. Actually, it is ensuring lifeline energy to all citizens at all times at an affordable price. So everybody has right to use energy to the extent that he needs for his survival there. And the goal is that we must have least energy to provide services as the energy efficiency term comes, and my previous speakers have already to do the same thing or use same appliances. So that is one way of doing that. Another thing is energy losses, which most of the appliances, most of the systems, we all know that the kind of sources of energy available to us at our hand to the society, we must explore the possibility of using non-renewable energy sources and also later on renewable energy sources. So coal, oil, natural gas, these are the well-known methods, but future lies in certain other forms of energy, particularly hydrocarbon energy, in coal bed methane and underground gasification, and natural gas hydrate. These are the three future ones, but CBM has already started giving results, and to some extent we are using part of it. Next please. This is a diagram which shows 20% is hydroelectric, and natural gas is projected to be increased to almost 20% from current 8%. Next. So what is the one slide I'm showing how the coal availability and coal uses are there. This is a major source of energy in India and likely to continue for another 15-20 years unless and until there is a energy processes, how the figure is changing from 304.56 it has gone to almost underground, but our compulsory is that we are producing at the current time from the reserves of coal energy. So we can't say that we have to go for others. Coal has to stay, but you are very right, sir, that R&D, although it is there, but not yet perfected. So unless it is perfected, the industries cannot use it. That's the question.
I'll go on to the next.
Thank you.
Okay.
So look here. Sir, take care, good. Thank you. ਹਾਂਜੀ sir, good. Okay, thank you.
Thank you, sir. Next in line we have
Rakesh Agarwal, going to talk about distillation.
Graciously agreeing to switch his spot with me. In case you're wondering, I'm Rakesh Agarwal and not Rakesh Gupta, even though both of us go long way back since 1970 when Professor K.S. Gandhi was our guru and we were the chelas, and he happens to be here, so it's a what I call conventional chemical engineering. Okay, thankfully done. Okay, so I will show you the multi-component distillation. Why distillation? Okay, distillation, percent of the energy consumed on the plant, anywhere between 40 to 60% is distillation, is separation. Okay, it's one of the largest component, and that's also true for the capital. 30% of the capital. Excuse me, can I just ask for a favor? Just that I'm giving a talk, be respectful, be quiet. I really appreciate that, because I think when I'm sitting in there, I had a really tough time understanding half of the talks. Okay, and I talk, when you see these configurations, this refers to a mixture. A is the most volatile component, C is the least volatile component, open circles are the reballers, filled circles are the incandescents. Okay, so that's the convention. Building the plant, you build the right one. Okay, so the first and the foremost question is, well, three components we know the field. When I was a graduate student, we knew quite a bit of the configuration. But the moment you move to four component separation, we really have no clue what we're talking about. We really do not know what the surface space is. What do I mean by surface space? What I mean is, how many configurations are there? Configurations, it looks like they have a purity restriction, right? Because if I feed BCD in this one column, and if I try to pull the middle component C here, chances are it will have B and a D. Okay? If I want to make it very pure, my reflux will be very high, very, very close to infinite. Okay, like it's so that's not possible, right? So what we were doing was we were simulating, right? So you write the programs, you start your simulations, then you ask the program to tell you pure A, B, and CD. And what the program did, okay, which we did not do ourselves, it decided not to have any C here and not to have any B here. Okay, that's the power of the mathematical optimization. Okay, so you're doing your optimization, you give a pure C and D, and you expect your flow rates to heat unit to go up very high, and the program suddenly prints an answer, and you look at it, wow, what happened here? And you realize, it decided to do a separation in the first column and took good away. Okay, so that was good. So that was a nice. Then you do the literature, you find out, someone published it in 1942. Okay, without doing any math, right? So
in reboiler section, heat is supplied, and in condenser section, heat is extracted. So both we can combine. So then better energy save possible.
And how do you combine that?
So this top product.
Distillation, right? Higher temperature at the bottom, you put the heat in, okay, you reject it at a lower temperature. So thermodynamically, you are putting the heat at a high temperature, rejecting it at a low temperature, and that's gives you the work for separation. Okay? So since it is the work at a heat at a lower temperature, if you want to put it back at the high temperature, the only way you can do it, I know, is a heat pump. Okay, and there are many ways of heat pump. You can stand here and talk for another 1 hour on that. And you could have a vapor recompression cycle, you could have a low pressure boiling on the bottom liquids. Okay. And basically when you're doing heat mass integration, you're taking some of the advantage, right? So when heat and mass integration I was doing, you had a B and you had a C, right? The condenser of the C had a higher temperature, the revolver of the B, and then you could put a section and you could connect it. So basically, your point is well taken. Wherever you have the heat, so I think in a general, if I could generalize, like whenever you have a heat and you have a condenser, if you can couple it, like, so it works out very well. But if in the same column, if you're doing it, then almost all the cases to this day, okay, the rank listing we have those top 10 from Aspen, and what we get from the